Welcome to The Explainer. Today, we're diving into a drug that literally changed the game for safety in the operating room. It's an amazing story, really, about how some seriously clever chemistry solved a problem that had been plaguing doctors for decades.
All right, so let's imagine for a second. Your surgery's over, everything went perfectly. What's the most critical thing that needs to happen right then and there? You might think it's just waking up, right? But it's actually something even more fundamental. It's about being able to breathe all on your own again.
And that right there, that's the post-surgery predicament we're talking about. See, waking up from anesthesia isn't as simple as it sounds. It's a really delicate dance, especially when you consider that for the whole operation, your body was intentionally medically paralyzed.
Okay, so during a lot of surgeries to keep you perfectly still, for things like putting in a breathing tube, doctors use these things called neuromuscular blocking agents, or NMBAs for short. And they do exactly what they sound like. They temporarily paralyze your muscles. Yep, including the ones that control your breathing. So the huge challenge has always been, how do you reverse that paralysis perfectly so your body can take over again? It's not just important, it's absolutely life or death. For the longest time, the way they reversed this was, well, let's just say it was kinda clumsy. The old school drugs, something like neostigmine, were pretty slow and you never quite knew what you were gonna get. There was always this nagging risk of not getting a full reversal, which could leave patients weak and struggling to breathe in the recovery room. And on top of that, they came with a whole laundry list of side effects, like a dangerously slow heart rate. It got so messy that you actually needed a second drug just to counteract the side effects of the first drug. Talk about a complicated balancing act. It was screaming for a better solution. And this is where our story gets really interesting. This old stubborn problem, it was about to run headfirst into a brand new and just incredibly elegant solution. And wow, this chart really shows you what a night and day difference we're talking about. Look at the mechanism, right? The old drugs worked indirectly, kind of like they were flooding the whole system, hoping to overpower the paralysis. But Sugammadex, totally different approach. It goes in and physically traps the paralyzing drug molecule. It just grabs it. And because of that, it's ridiculously fast, it's super targeted, and it works even if someone is in a deep state of paralysis, which, by the way, was basically impossible to reverse quickly before this.
So how in the world does it actually do that? Well, the secret is all in its shape. It's so unique that it's actually earned the nickname the donut drug. And it's just this beautiful example of how a really clever bit of chemistry can create an instant, life-saving fix.
So what exactly is Sugammadex? Okay, so at its heart, it's what's called a modified gamma-cyclodextrin. I know, that's a mouthful, but you can just think of it as a ring of sugar molecules. The real genius, though, is its structure. It's literally shaped like a tiny, hollow donut. And that hole in the middle, it's been perfectly designed to be the ultimate trap for a couple of very specific muscle relaxant drugs.
This whole process has a cool name, chemical encapsulation, and it's just brilliant. So, these little Sugammadex donuts start floating around in your bloodstream, and they're on a mission, hunting for those muscle relaxant molecules. Then, bam, step 2. The relaxant molecule finds a donut and fits right inside that hollow center. It's a perfect fit. They form this super tight, super stable complex, like a hand fitting perfectly into a glove. And just like that, the muscle relaxant is completely neutralized. It's trapped, it can't do its job anymore, and your muscle function comes roaring back almost instantly.
You can probably imagine, this incredible mechanism gives anesthesiologists a level of control they just never had before. It's like having the ultimate safety net. They can fine-tune the reversal with incredible precision, based exactly on what the patient needs in that very moment.
And check out this level of control. If a patient's already starting to wake up a bit on their own, a small dose of 2 milligrams per kilogram gets the job done in about 2 minutes. But what if they're in a deep paralysis? That situation where the old drugs were basically useless. No problem. A 4 milligram per kilogram dose works in just 3 to 5 minutes. It's amazing. And then there's the rescue dose.
Okay, this is the big one, the rescue dose. We're talking a massive 16 milligrams per kilogram. This is a true, honest-to-goodness lifesaver. Think about the absolute worst-case scenario. A patient has been paralyzed, but for some reason the doctors can't get a breathing tube in. It's the can't intubate, can't ventilate nightmare every anesthesiologist dreads. This dose can reverse that profound paralysis in less than 3 minutes. It takes what could be a catastrophe and makes it manageable. Just incredible.
But listen, like any powerful tool in medicine, we've got to look at the whole picture, right? It's not all sunshine and roses. So let's talk about the amazing benefits, but also get real about the important considerations.
The pros are huge, no doubt about it. The reversal is just so much faster and way more predictable. Doctors can finally reverse that deep blockade whenever they need to. And because it's so targeted, all those nasty side effects from the old drugs, gone. Which means you don't need that second drug anymore. It's basically wiped out that scary problem of patients waking up still feeling weak or paralyzed.
But it's not perfect. For one thing, there's the cost. It is way more expensive than the traditional agents. That's a big hurdle. Also, since it's flushed out by your kidneys, it's generally not recommended for anyone with severe kidney failure. And while it is very rare, there have been reports of severe allergic reactions, even anaphylaxis. So yeah, it's an amazing tool, but it's one that definitely demands respect.
And speaking of things to be aware of, there is one super important drug interaction that's critical to know. Because Sugammadex is so good at trapping certain molecules, it can accidentally trap the hormones from birth control too. This can make hormonal contraceptives way less effective. The advice here is crystal clear. If you get Sugammadex, you need to use a backup, non-hormonal form of birth control for the next 7 days. That's a really important takeaway.
So when you step back and look at the whole story, it's so clear that this drug wasn't just another small step forward. Its arrival really marked the beginning of a whole new era of patient safety in the world of anesthesia.
And you don't have to take my word for it. This quote from the medical literature really just says it all. It's called a paradigm-shifting agent. That's a huge deal. It means it didn't just improve an old idea, it completely changed the game. It fundamentally altered how anesthesiologists approach and manage what is one of the most critical moments in any surgery.
At the end of the day, it comes down to this. By giving doctors a level of control, speed, and safety that was honestly just unimaginable before, Sugammadex has made surgery safer for millions and millions of people. It took the unpredictable art of waking someone up from anesthesia and turned it into a reliable, predictable science.
Which kind of leaves us with one last question to chew on. Sugammadex solved a problem that seemed totally impossible for decades, and he did it with nothing more than a really clever piece of chemistry. It just makes you wonder, doesn't it? What's the next impossible problem in medicine that's just waiting to be solved by a little bit of elegant chemistry?